Hello, and welcome to this tutorial where we'll show you how to use the Antibiotic Resistant Target Seeker, or ARTS, to screen for potential resistance genes in bacterial genomes. This video is divided into two main parts. First, we'll give you a brief introduction to how ARTS works. Then we'll upload a set of Salinispora genomes and guide you through both the single genome and multi-genome views. As an example, we'll focus on the Salinosporamide biosynthetic gene cluster and its associated resistance gene. The idea behind ARTS is based on a simple but powerful concept. Bacteria that produce an antibiotic must also protect themselves from it, either by exporting the antibiotic, modifying it, or altering the target protein so the antibiotic can't bind. So how can ARTS help us find these self-resistance genes? ARTS starts by identifying core genes, genes that are essential and thereby found in at least 90% of species within a given phylum. It then checks these core genes for three key features commonly found in resistance targets. Duplication. Resistance genes often have extra copies, so ARTS looks for duplicated core genes within a genome. Proximity to biosynthetic gene clusters. Signs of horizontal gene transfer. Resistance genes are sometimes acquired from organisms. ARTS compares the phylogeny of each core gene to the species tree to detect this. Let's start by uploading some example data. Click Start Query to go to the upload page. At the top, you'll see some server statistics. This gives you an idea of how busy the system is. The runtime of your job may vary depending on the queue. Next, we need to define whether each file contains a single genome or multiple genomes. In our case, each file contains a single genome. Now we can start the upload. A quick tip: if you try to upload too many genomes at once, for example 20, the upload may fail. It's better to upload in smaller batches, up to 10 genomes at a time. And don't forget, this is often overlooked. You need to click the upload button to finalize the upload. If you already have antiSMASH 5 results, you can upload those directly to save some runtime. In the General Settings section, you can enter a job title. We'll call this run Tutorial Video 1. You can add your email address to get the results link via email. The most important step here is to pick the correct reference set for your genomes. Make sure all uploaded genomes belong to the same phylum. If you're working with metagenomic data, you can use the metagenome reference set, which is based on a smaller, curated set of essential genes. In our case, all genomes are from Salinispora, so we'll use the actinobacteria dataset and keep the phylogeny screen enabled. The resistance model screen is enabled by default and checks for known resistance genes. The domains of unknown functions screen highlights domains of unknown functions within the biosynthetic gene cluster. While DUFs don't tell you much directly, they might be interesting for exploratory purposes. The exploration mode skips filtering out core genes that are involved in transport, regulation, or biosynthesis. You'll get more hits but also more false positives, so use it with caution. Under Advanced Settings, you can adjust cutoffs or upload your own HMM models for resistance or core genes. For this tutorial, we'll stick to the default settings and submit the job. ARTS runtime varies, typically between 5 to 30 minutes per genome. This depends on job size and server load. You can revisit your results later by saving the page link or searching for your job title on the upload page. We already have some pre-computed results ready. Let's open the results for our job titled Salinispora dataset and click View Report. At the top, you'll see a summary table with basic info for each genome. Clicking on an organism opens the individual genome view. Here we'll look at Salinispora tropica. You'll find an overview of the genome including total number of genes, number of essential genes, number of BGCs, hits to known resistance genes, and summary of ARTS screening hits. Below is the main essential genes table. Each row lists a core gene, its function, and how often it appears across species, the ubiquity. The columns D, B, and P indicate whether the gene meets ARTS criteria. D duplicated, B. near a biosynthetic gene cluster, P. shows signs of horizontal gene transfer. Additionally, genes homologous to known resistance genes are shown. Use the sorting arrows to bring hits with multiple criteria to the top. In this case, we find the 20S beta proteasome subunit. It meets all 3 ARTS criteria and is associated with a known resistance gene. This makes it a strong candidate. Click the plus icon to expand the row and see gene ID, contig and location, links to the BGC and Phylogeny analysis. Clicking on the BGC link opens a view similar to antiSMASH. Main biosynthetic genes are shown in red, core genes in yellow, matches to known resistance models in light green, matches to known resistance that are also classified as core genes in purple. Here we see the salinosporamide BGC and the altered copy of the 20S beta proteasome subunit that functions as a resistance gene. Going back to the essential genes table, we now click to view the phylogenetic analysis. On the left is the species tree and on the right the gene tree. You can see that in the species tree the uploaded genome clades with other Salinospora genomes. In the gene tree, you see the 2 copies of the 20S beta proteasome subunit. One clusters with other Salinispora strains, that's the original version. The second copy clusters differently, which suggests horizontal gene transfer, fulfilling the 3rd ARTS criterion. Now, let's go back on the results page. We switch to the multi-genome analysis. The essential gene table shows a table similar to the single genome view, but summarizes data across all uploaded strains. Here, the number indicates the proportion of strains with gene duplication, proximity to a BGC, and signs of horizontal gene transfer. Use the search bar to find the 20S beta proteasome subunit and click the plus icon to expand the row. This reveals which strain meets the ARTS criteria. In our case, both Salinispora tropica CNB 440 and Salinispora tropica CNT 250 have hits for all 3 criteria. To see if these hits belong to the same gene cluster, we use the BiG-SCAPE network analysis integrated into ARTS. BiG-SCAPE groups similar BGCs into gene cluster families, GCFs. We see both resistance genes are linked to GCF3. Scroll down to the BiG-SCAPE analysis overview, sort by GCF number and expand GCF3. Both gene clusters include core hits for the TigerFam 03690 domain, the 20S beta proteasome subunit. We can either explore the cluster directly in the single genome analysis page, which is linked in the table, or go directly to the BiG-SCAPE gene cluster network. This opens the link to the BiG-SCAPE analysis of our uploaded genomes. Since our cluster is a PKS-NRPS hybrid, we use the hybrid network view and search for the cluster by name. This shows it in the context of its related clusters. Finally, back on the results page, you can export trees, tables, and alignments. All results can be downloaded as a zip file. Data is stored on the ARTS server for at least 1 month. That's it. We hope this gave you a clear introduction on how to use ARTS to mine for potential resistance target genes. Keep in mind that the more ARTS criteria a gene meets, the more likely it is to be a resistance gene. But it is still a screening tool. Not all hits are true resistance genes, and exceptions are common in real data. Thanks for watching, and good luck with your own genome analysis.